Blazing temperatures that defy imagination erupt across the cosmos, and the most extreme of them all hides at rank 1, a phenomenon most people never even consider. Stay tuned as we count down to the ultimate hot gas stream that reshapes our understanding of energy. Blazing from the moment a rocket ignites, the engine exhaust creates a superheated gas stream that can reach temperatures exceeding 3,000 degrees Celsius, rivaling the surface of the sun. Engineers design nozzle geometries to channel this plasma efficiently, converting thermal energy into thrust that propels payloads beyond Earth. The exhaust plume expands supersonically, forming shock diamonds that shimmer in the upper atmosphere. Researchers study these flows to improve propulsion and to understand how high-temperature gases interact with surrounding air, which is crucial for reducing acoustic impact on launch sites. As we watch these fiery jets, the next entry will show a solar phenomenon that outshines even this engineered inferno.
Imagine a burst of solar energy that hurls plasma at millions of degrees, launching jets that race across the sun's surface at speeds up to 3,000 kilometers per second. Solar flare plasma jets are driven by magnetic reconnection, where twisted field lines snap and release colossal amounts of stored energy. These streams can heat surrounding gas to over 10 million degrees C, creating bright X-ray emissions observable from Earth. Scientists monitor them closely, as they can spew charged particles toward our planet, potentially disrupting satellites and power grids. Understanding these jets helps refine space weather forecasts, safeguarding modern technology. Up next, a cosmic explosion leaves behind a remnant that still glows with intense heat, far beyond what we see on our star.
Surprisingly, when a massive star ends its life in a supernova, the expelled material forms shock fronts that heat interstellar gas to temperatures of tens of millions of degrees Celsius. These superheated streams, visible in X-ray wavelengths, expand outward at thousands of kilometers per second, shaping nebulae and seeding the cosmos with heavy elements. The Cassiopeia A remnant, for example, showcases filamentary structures where plasma temperatures are estimated at around 20 million degrees C, making it one of the hottest known astrophysical objects aside from active galactic nuclei. Astronomers study these remnants to trace the life cycle of matter and to test models of high-energy physics under extreme conditions. Coming up, we descend to a galaxy's core where a black hole powers a jet even more focused and hotter than any supernova shock.
Hidden deep within the galaxy M87, a supermassive black hole launches a relativistic jet that streams plasma at near-light speeds, heating the gas to estimated temperatures of several billion degrees C. Though the black hole itself swallows everything, magnetic fields in its accretion disk funnel some of the infalling material into narrow beams that pierce the host galaxy. Observations by the Event Horizon Telescope suggest these jets contain particles energized by the black hole's spin, producing synchrotron radiation across the spectrum. The extreme temperatures and velocities offer a natural laboratory for testing Einstein's relativity and plasma physics. While these cosmic behemoths dominate the universe's energy budget, the next entry brings us closer to home, to a volcanic moon whose eruptions generate astonishingly hot gas plumes.
When Jupiter's moon Io erupts, its volcanoes spew sulfur dioxide gas that can be heated to roughly 1,500 degrees Celsius, creating towering plumes that rise hundreds of kilometers above the surface. Tidal forces from Jupiter's massive gravity flex Io's interior, generating enough friction to melt rock and drive explosive eruptions. The resulting gas streams, though cooler than stellar jets, are among the hottest volcanic outputs in the solar system. Their composition and temperature help scientists understand how tidal heating shapes planetary geology and influences Jupiter's magnetosphere, as the plumes inject charged particles into surrounding space. From this moon's fiery breath, we shift to Earth's own hidden furnace, where heat rises from deep within the mantle, forming a spectacular but less visible gas stream.
Few people know that beneath Earth's crust, mantle plumes act as subterranean elevators, transporting superheated rock and gas upward at temperatures estimated around 1,800 degrees Celsius. These upwellings manifest on the surface as volcanic hotspots like Hawaii, where basaltic lava emerges after traveling thousands of kilometers through the mantle. The gas component, primarily water vapor and carbon dioxide, expands dramatically as it nears the surface, creating localized atmospheric streams that can affect regional climate. Geophysicists study these plumes to decode Earth's thermal evolution and to predict future volcanic activity. While the mantle's furnace is hidden, its influence reaches far and wide. Next, we examine a terrestrial phenomenon that flashes across the sky in an instant, heating the surrounding air to astonishing levels.
At the heart of a thunderstorm, lightning carves a plasma channel that momentarily reaches temperatures of about 30,000 degrees Celsius, 5 times hotter than the surface of the sun. This rapid heating ionizes the surrounding air, creating a conductive path for the electric discharge. The intense burst lasts only a few microseconds, yet it generates powerful shock waves we hear as thunder. Researchers capture high-speed footage to study the dynamics of this transient superheated gas, revealing insights into electrical breakdown and atmospheric chemistry. The fleeting nature of lightning makes it a unique natural laboratory, bridging terrestrial weather and high-energy physics. Following this brief blaze, we turn to a controlled, continuous source of plasma that powers modern industry.
Only a handful of manufacturing processes rely on plasma torches that generate gas streams, heated to roughly 20,000 degrees Celsius, hot enough to melt steel in a split second. By passing an inert gas like argon through an electric arc, the torch creates a focused plasma jet that can cut, weld, or coat materials with precision. Engineers monitor the temperature and flow characteristics to optimize efficiency and minimize wear on equipment. While these devices mimic natural high-temperature phenomena, they do so in a controlled environment, allowing scientists to experiment with plasma chemistry and material interactions at extreme conditions. As we move closer to harnessing fusion energy, the next entry showcases the cutting edge of plasma confinement.
When a tokamak confines hydrogen isotopes, it creates a swirling plasma that can reach temperatures of over 100 million degrees C, hotter than the core of the sun. Magnetic fields twist the ionized gas into a torus, preventing it from touching the reactor walls. This superheated stream is the key to achieving nuclear fusion, where atomic nuclei merge, releasing vast amounts of energy. Researchers at Diğer and other facilities measure the plasma's temperature, density, and stability to push the technology toward a sustainable energy source. Though still experimental, these plasma streams demonstrate humanity's ambition to replicate stellar conditions on Earth. Finally, we arrive at the most extreme natural jet known, a cosmic fireball that dwarfs all previous examples.
Finally, the universe's most ferocious gas stream emerges from a gamma-ray burst, where a collapsing massive star or neutron-star merger launches a relativistic jet that can heat surrounding material to billions of degrees Celsius. This jet, traveling at near-light speed, releases a flash of gamma radiation brighter than an entire galaxy for seconds, while the internal shock waves accelerate particles to ultra-high energies. Observations suggest the jet's core temperature may exceed 10·12 degrees C, making it the hottest known flow in the cosmos. Studying these bursts helps astrophysicists probe extreme physics, test theories of gravity, and understand how heavy elements are forged across the universe. The sheer scale of this superheated stream reminds us how much more there is to explore beyond our own planet.
We've traveled from the controlled fury of rocket exhausts to the mind-bending relativistic jets of gamma-ray bursts, witnessing how each superheated gas stream reveals hidden layers of physics and cosmic history. These extremes not only push the boundaries of temperature but also teach us about matter under conditions we can scarcely replicate on Earth. If you enjoyed this deep dive into nature's hottest flows, hit like and subscribe so you won't miss our next list of astonishing scientific wonders. Which stream left you the most awestruck? Share your thoughts below. I love hearing your perspectives. Thanks for watching, and see you in the next video.